Hi, my name is Darshan and I'm a private tutor of math and physics. In this video, we'll talk about AP Physics 1 2023. It's an interesting question based on the simple harmonic motion. The question is right in front of you. So let's read this out. It says that a cart on a horizontal surface is attached to a spring. So this is the cart and this is the spring which is attached over here, and the other end of the spring is attached to a wall. So this is wall over here and the spring is attached to it. The cart is initially held at rest as shown in figure 1, and when the cart is released, the system consisting of the cart and spring oscillates between the points plus L and minus L. So clearly that's a simple harmonic motion of the spring mass combination oscillating between negative L and plus L, of course. In figure 2, it shows the kinetic energy of this cart spring system as a function of the spring's potential energy. So that's interesting. They have graphed the kinetic energy versus the potential energy, and it particularly is a linear curve with a negative slope. Friction forces are negligible. On the graph of the kinetic energy versus the potential energy shown in the figure 2, we have to, the values of the x and y intercepts are same. Of course, we can clearly see y intercept is also 4, x intercept is also 4. So they're asking us to justify this using the physics principle. I think the justification is pretty straightforward because there are no frictional forces, right? So can we say that there are no non-conservative force? So we can say that the non-conservative forces are equal to 0. And if there are no non-conservative forces, can I also say that the mechanical energy of the system is conserved, right? The mechanical energy of the system is conserved. So it makes absolute sense that at when the kinetic energy was 4, and can you remind me when is the kinetic energy maximum? Is that at extreme mass or is that at equilibrium? At equilibrium, not an extreme mass, because at extreme mass the speed is 0 and the amplitude is maximum, and at the equilibrium, as in at x equal to 0, the amplitude, I mean the elongation is 0, so the displacement is 0 while the velocity is maximum. So this k equal to 4 joules corresponds to the point of x equal to 0, and this 4 joules of potential energy corresponds to the point of either extreme mass. So it makes absolute sense that their intercepts are same, because it indicates that whatever kinetic energy was at the equilibrium, that same kinetic energy got converted completely into the potential at the extreme mass, because mechanical energy is conserved. So that is the reason why the kinetic energy and potential energy curve has the same intercepts. I hope that makes sense. Let's jump on to question number part B of the same question. Oh, this is interesting. They are pretty much mixing momentum in SHM. When the cart is at plus L and momentarily at rest, this is really important, momentarily at rest, a block is dropped onto the cart as shown. We can clearly see that a 3m0 block is dropped on the block m0, and the block sticks to the cart, and the block cart spring system moves and continues to oscillate still between negative L and L, right? So amplitude doesn't change. The masses of the cart and the block are m0 and 3m0 respectively. That's fine, we can see it. If the frequency of oscillation before the block is dropped onto the cart is f1 and after it is dropped is f2, then what is the numerical value of the ratio of f2 over f1? Let's remind ourselves, what is the formula for the frequency of spring mass system? Well, I do remember the formula for the time period. It's 2 pi root m over k. So obviously the frequency is just going to be 1 over t, right? So it's 1 over t, which is 1 over 2 pi root of k over m, because I just took the reciprocal, right? So 2 pi came at the denominator and m over k became k over m with a square root over it, right? So this is the usual formula for the frequency. So what is the frequency f1? F1 is simply when m is m0. So F1 is 1 over 2 pi root of K over m naught. And what is the value of F2? So in F2, nothing changes except the mass, because the total mass which is oscillating now is 4m naught. So the F2 will now become 1 over 2 pi root of K over 4m naught, not 3m naught, because the total mass will be obviously 4m naught. So this is 4m naught over here. It's good to see 4 because square root of 4 is 2, right? So I'm going to write this as 1 over 2 pi times 1 over 2. Why the 1 over 2? Because the square root of 4 is 2. And then root of K over m naught remains as it is. All right. They need the ratio of F2 over F1. So that's what we're going to do. F2 over F1 is going to be there you go. In fact, there is a better way to find the ratio. In fact, we can do it like that as well. Doesn't really matter. So F2 is 1 over 2 pi times 1 over 2 times root of K over m naught over F1 from here is 1 over 2 pi times root of K over m naught. If we notice carefully, 1 over 2 pi and 1 over 2 pi is gone. Root of K over m naught and root of K over m naught is gone. All we are left with is 1 over 2, which is or should be our final answer. So F2 over F1 is 1/2. That should be the answer to this question. All right, let's move on to the next part. Here they say that the dashed line in figure 4 shows the kinetic kinetic energy versus the potential energy of the block cart system after the block is dropped onto the cart. So even after dropping, their energy is not changing. That's interesting. This graph is identical to the graph, of course, for the cart spring system before the block is dropped. So we have to explain that why they are same using the physics principles. So that's same because if we go back, right at the time when it is dropped, we know that the momentum should be conserved, right? So if it is conserved, the initial momentum should be equal to the final momentum. Notice carefully over here, what do they say? They say that when it is dropped, m naught was at rest. It means that after dropping 3m naught as well, the system should be at rest, so that the initial momentum is 0. And right after dropping, the final momentum should be 0. So its speed or the velocity should be 0. Okay. So if its velocity is 0, and since this is the extreme point, what is the only energy in this particular system? Isn't that just potential? Because the potential energy is spring potential is K over 2 x naught square. And what is x naught? X naught is L, because this thing happens at x equal to L. So don't you think still after dropping, just at that instant, the total energy is K over 2 times L square? And isn't this same as the previous one, where it's still the potential energy is K over 2 L square, which has a value of 4 joules, right? So that is the reason why the total energy is still 4 joules. And since still the mechanical energy is conserved, because there is no external force. Obviously, the friction is already being ignored. They are already saying that you have to ignore the friction. So there is no non-conservative force. Mechanical energy is conserved. Since amplitude remains same, momentum is conserved. At the extremas, the energy is same as the previous one, and hence the total energy just remains the same. That is the justification of why the two curves are identical in this particular case. There's another way in which you can explain it. The maximum velocity, if we remember the formula, is omega times a, right? Okay. Now, what is omega? Omega will change, right? Omega is root of K over m. So it's K over 4m naught, because the total mass is now 4m naught, and amplitude is still the same. So what is the maximum kinetic energy at the equilibrium? Obviously. So K max is going to be half m. This is where we have to be careful. Half mv square. And what is m? M is 4m naught. And if we do v square, we have to do root of k over 4 m naught times a whole square. So if we open this up, this becomes half of 4m naught times k a square over 4m naught. And fortunately, 4m naught and 4m naught is still cancelled, and we once again end with 1 over 2 k a square, which is nothing but what we got over here, because amplitude is obviously L, so I can replace amplitude with L, and we can clearly see that these two energies are still same. So either you can justify using the, obviously because AP Physics 1, they go with the rubric and everything is stepwise marking. So if you want to show the math, obviously you can do this and you will get full credit. Otherwise you can write it as a qualitative fashion, or whatever I have said, the justification, along with mechanical energy conservation and all of that. Still you will get the full credit, right? So this is how we can answer this particular question. I hope it makes sense. Let's go to, I think this is the last part. So this is the, in fact, this is part C, part 2. Okay, after the block is dropped onto the cart, consider a system that consists only the cart and the spring. So no cart and the spring, as in not the block. What is the block? If you are getting confused, a block is dropped. This is the block, right? This guy is the block. Let me highlight that with a different color. This guy is block. So now they are asking us to ignore the block, right? They are asking us to treat only m naught and the spring as a system. All right, okay, we can do that. So only the cart and the spring is our system now. And on figure 4, as in on the same figure, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped onto the cart. This is a really interesting question where we are going to borrow the work which we have done earlier, because we know that the maximum speed is this. However, what is the maximum kinetic energy just of the cart spring system? Because at equilibrium, obviously there is no spring energy, right? It's the maximum kinetic. So if we now find the value of the maximum kinetic energy, that's going to be half. Now the mass will be m naught, because remember we are only taking the cart, not the block, and the block was 3m naught, which is ignored. So m is still m naught, while v remains same, right? Because both the cart and the block have the same velocity. And we already found in the previous question, it's this one. So I'm gonna write that over here, k over root of k over m naught times what was that, a, and a is L, right? Amplitude, so that's square. So this is gonna be equal to half m naught k over 4 m naught L square. M naught and m naught is gone, so we are left with 1/8 of KL square. Actually, there is a better way to write this, to understand this intuitively. I'm going to write that as 1/4 of 1/2 KL square. Why? Because this makes a clear sense that now the maximum energy is 1/4 of the initial energy, because half KL square was the initial energy, right? Here you go. This is the initial kinetic energy. So this is 1/4 of the initial kinetic energy maximum. And do you think the maximum potential will change even if we change our system to cart and spring? No, because the maximum potential is only dependent on the spring, and the spring is still a part of the system, right? Still a part of the system. So the maximum kinetic energy will still be, maximum potential energy will still be a 1/2 KL square, since the spring is still a part of the system. However, the maximum kinetic energy will now be only 1/4 of the initial. What was the initial? 4. What is 1/4 of 4? It's 1. So the solid line is going to look like this. It starts from 1 now, and it still goes to 4. So this is how the kinetic energy versus the potential energy of the cart spring system is going to look like. I hope this question makes sense. It was not difficult, entirely conceptual. question is based on an inclined plane, a cart, and a position versus time curve. This is what we can see in a bird's eye view. Let's read it out. Students conduct an experiment to determine the acceleration of a cart. So this is a cart over here. It's rolling down, and we have to determine the acceleration of the cart using an experiment. The cart is released from rest at the top of the ramp at t equal to 0 and moves down the ramp. The x-axis is defined to be parallel to the ramp with its origin at the top. So this is where the origin is. Oops. This is where the origin is, and this is where the plus x-axis is to be considered. And students collect the following data as shown. So they collect the position of the cart versus the timestamp at that particular position. So that's an experiment. What they ask as part 1 is indicate which quantities could be graphed to yield a straight line whose slope could be used to determine the acceleration of the cart. You may use the remaining columns in the table as needed to record any quantities including units that are not already in the table. So this is a classic question on the equation of motion. If we remind ourselves, the second equation of motion is to be defined as x is equal to v initial times t plus half a t square, right? We are interested in the value of, unfortunately, the initial velocity is 0 because it is released, where was that? It's released from the rest at the top. So fortunately, vi is 0. So the equation boils down to half a t square. And we have the value of x. All we need is the value of t square so that its slope will be equal to half of a, which can definitely be defined as which can definitely help us to find the slope, find the acceleration, right? Although we can definitely go ahead and rewrite it or manipulate like this and consider this as our x variable, that is totally fine. We can graph t over t square over 2 as well, but it does not mean that if we do this, that is incorrect. That is absolutely correct as well. So I'm going to adopt the first one where I find the value of t square, and I'm going to write it over here. So just bear with me for a couple of minutes. In fact, you can fast forward this portion of the video as well because I'm just using my calculator over here and just finding the value. So that's going to be, the first one is going to be 0.1521. Then I'm going to have 0.59 square, which is 0.3481. Then 0.77 square is going to be 0.5929. 0.96 square is going to be 0.9216. Then 1.2 square is going to be 1.44. What we have over here is t square with the unit as second square as well. So this is what we have. On the vertical axis, we will have the position. Let's write it very clearly over here. And on the horizontal axis, we'll have t square or perhaps the time square. This is in meters, of course, and this is in second square. So this is how we are going to graph it. All right. In the next question, indeed, they're asking us to graph the same thing. So I think it would be helpful for us if we can just take this as well over on the next page so that we see what we have to graph, of course. On the y-axis, we will clearly have the value of position. So this is where our grid line is going to look like, plus x and minus x-axis, of course. Let's see, how can we define the units? It goes from 0.06, 0.14, 24, 3755. I think 0.1 units on each of the grid position on the y would suffice, because if this is 0.1, 0.2, 0.3, 0.4, 0.5, I think that will work, because 0.55 will also be right in the middle of 0.5 and 0.6. So I'm going to mark that over here. So this is 0.1, this is 0.2, this is 0.3, this is 0.4, 0.5 and 0.6 over here. Obviously what I'm showing over here is the position along with the unit of meters, and here what I'm showing is time square along with the unit of second square. Over here I have let's see, the smallest one is 0.3, then 0.5, then 0.9, then 0. Okay, the smallest one is 0.1, so that's actually is in increasing order. I think 0.1, no, I don't think so. 0.1 will work. Will 0.2 work? 2, 4, 6, 8, 1, 1.2. I think yes, 0.1, 0.2 will work. So we mark it as 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, and 1.4. Excellent. Let's mark the points. So the first point which we have is I believe 0.06. So 0.06 is just near the 0.05 mark. Each mark corresponds to 0.02. So 0.06 is this one, and 0.1521. So this is 0.2. It means that it is 0.04 each of the marking. So 0.04, 0.04, 0.08, 0.12, 0. Sorry, this seems to be like 1, 2, 3, 4 markings. So that's actually 0.5. So if this is 0.5, then this is 0.5, 1, 1.5. 1.5 is over here. So this should be our first point. Okay, the next point is 0.14. So this is 0.1, 1, 2, and 1, 4. This is 1, 4 over here. This is 0.14. I'll just keep marking over here as well. This is 0.06. And this is 0.35, around 0.35. So this is 0.2, 0.25, 0.3, 0.35. This is 0.35. 0.35. The earlier one was 0.15. This is 0.15, and this is where the next point is going to be. The next point is over here. We have 0.24. So this is 0.24. Okay, so that was lost the track. 0.04. Yeah, so 0.24 is right here, I think, because 28, then 0.04 is will be 2 segments. So 0.22. This is 0.24. 0.24. Okay, and the x-axis is 0.6, around 0.6. So 0.6 is right over here. 0.6 will be over here. The next one is 0.37. So 37 will be 0.32, 34, 36, 38. So 37 will be right in the middle, somewhere over here. This is 0.37, and the corresponding axis 0.92. 0.8 is here. So this is 8.5, 9, and 9.5. So 9.2 is somewhere in the middle, maybe somewhere over here. So this could be that point. I'm sorry, not this. A little bit up. A little bit up will be somewhere over here. Okay, not bad. And then 0.55. So 0.52, 54, 56. So 0.55 is somewhere over here. I'll just draw a line so that I keep a track of where I am. And then I have 1.44. This is 1.4, 1.45. So 1.45, near to 1.45 is somewhere over here at this point. So I'll just do away with the dotted line over here. All right, and then I just draw the regression model, right? To draw a straight line, they want us to draw the regression line, and it starts from, at 0. It is at 0 at the top, so it starts from the origin. And okay, the regression line looks pretty cool. It's somewhere, okay, no, yellow doesn't look cool, maybe blue. So it's somewhere over here. Okay. Okay, this looks like the line of best fit. Excellent. Let me mark the points over here. It's 1, 2, 3, 4, 5. So that's easy for us to keep a track. All right, having said that, the next one wants us to use the same line and calculate an experimental value for the acceleration as it rolls down. Okay, so that's easy, right? We are just looking for the slope, but remember that we have to use the line. we have to use the regression model, not the points of the experiment. So we just find any 2 points which we feel like are on the curve or on the straight line. So that's going to look like any decent intersection points. That's what we are looking for. So I think let's see, can we take where do I see a grid intersection? Over here I do see a point which is right here, in fact right here, and this point is, if this is 0.2, this is 0.25, so its x coordinate is 0.25 and its corresponding y coordinate is 0.1, so that is one of the point. And the next point is going to be let's see, perhaps somewhere over here. This looks like a reasonable point. Yeah, not bad. We can take that. So this looks like, what was that? So it was somewhere over here. Yeah. So this point is a little close to 1.35 as its x value, 1.35, and its y value is 0.52, 0.52. All right, so these are the two values which I have. If I use my calculator to find the slope, it's 0.52. The slope is going to be 0.52 minus 0.1 over 1.35 minus 0.25. So 0.52 minus 0.1 over 1.35 minus 0.25, which is 0.38. But remember, this is not the answer, right? I'm in fact going to take all this over on the next page as well, because that's where our question is, so that we can keep a better track. All right, so this is all the work for this question, but remember that this is only half of this value, because the slope is half of a. So our answer is going to be, since half of a is 0.38, acceleration is just going to be twice of this. So 0.38 multiplied with 2 is 0.76. 0.76 meter per second square is going to be the acceleration, the experimental value, of course, of this experiment. Hope this makes sense. In the next question, the students are asked to determine an experimental value for the acceleration due to gravity using this particular data. So which additional quantities do the students need to measure in order to calculate G experiment from A? I'm just gonna pull up this situation, this image as well over here. Okay. Now, it is nowhere mentioned in the question that there is no friction, so we cannot just ignore it. And in fact, this is an experiment, right? So definitely these are realistic terms. There will be there will be a friction, there will be an air resistance. So let's say the net force, which is with which this is getting stopped, friction and air resistance, that is represented with F, and there we have a normal reaction Fn. And obviously the mg, the gravity is going to act right down, but we are going to make it its components, because this is an inclined plane, so we are interested in along the x-axis and perpendicular to the x-axis. This is going to be theta, so this is going to be mg sine of theta, and this is going to be mg cos of theta. These are going to be the components and the FBD. And of course, the acceleration is right here. So can we say that the normal reaction is actually equal to mg cosine of theta? And can we also say that mg sine theta minus F is equal to ma? You can say this, right? Are we given the value of m? Let's find out. No, the mass of the cart is not given anywhere. All right, so the value of, but we are not done yet. We are not saying that we need the mass. We know that the friction is mu times normal reaction, and the normal reaction is just written right over here for us. So if you're going to plug the normal reaction back in, we are going to have mg cos theta is equal to ma. M is gone from all the sides, so we do not need mass. And if we flip the equation, then the acceleration experimental will be equal to the g sine theta minus mu g cos theta. And since we are interested in g in terms of a, so let's isolate g because we already have the value of a. So g a experiment is going to look like g is taken out, we have sine theta minus mu cos theta, and finally the value of g is going to be a over sine theta minus mu cos theta. All right, so here the value of let me just, this looks a little bit confusing, the g comes right over here. Okay, so obviously to find the value of g experiment, we already have the value of a experiment. However, we need to know what is the value of mu of the surface. So that's not something which we measure, right? That will just be something we just need to know what type of, the surface that is, and we just need to find out from the internet that what is the corresponding value of mu for it. But what we need to measure is the value of the inclination of the plane, which is theta, right? So what additional quantities? I will say that we need to measure what is the type of surface of incline, so that we can find mu, and we need to measure the value of theta so that we can just plug everything back in over here and we can find the value of g experiment. All right. Write an expression for the value of g. We already did that. This is the expression for the value of g experiment in terms of a, which we already found. All right. I hope this makes sense. Here they are asking that what is the physical, so the students calculate the measure of the value of g experiment to be significantly lower than the accepted value of 9.8. So what is the physical reason other than the friction or air resistance that could lead to a significant difference in the experimentally determined value of g? Let's write what was the expression once again. So the value of g was a over sine theta minus mu cos theta, sine theta minus mu cos theta. If the friction and the air resistance effects are ignored, other than that value, I think the only reason which I see as per this is an incorrect value of mu, because it's very difficult to estimate that what kind of surface that is in actual, and then finding the value of mu, corresponding value of mu. Maybe the surface is uneven and it has different value of mu entirely on the complete, incline. So that can be one of the reason that mu is not constant. However, we have taken it to be a constant. And the other reason is, since we have determined the value of theta as an experimental measure, maybe we measured theta incorrectly. So maybe the value of theta is incorrectly measured. That can be one of the reason as well. What can be a physical reason? Well, I was thinking that maybe we calculated the value of theta in radians or degrees something, but that's not really a physical reason. So we'll skip writing that. I think this would suffice. These could be the two reasons which we think are that could lead to a significant difference in the value of g. And briefly explain how the physical reason you identified with part C would lead to a decrease in the value. Okay, so it would lead to a decrease in the value if the value of the denominator is more, right? Because if this is more, then g will be less. And when will it be more? When theta is more, because sine is an increasing function. If we increase the value of, this is a tricky one, if we increase the value of theta, Sine theta will increase, however cos theta is going to decrease because cos is a decreasing function. So sine minus cos, sine minus mu times cos will eventually increase, and a over an increased value will decrease. So if we measure theta to be, or the incline to be, more steep than what is actually is, then the value of g is going to be significantly lower because the denominator is going to increase. So explain how the physical reason we measure theta to be more than the actual, so we measure it to be more steep than what that is. So the steepness is actually a reason why the g experiment could be less. All right, the last one talks about that the student wants to confirm that the acceleration is the same whether the cart rolls up or down the incline. So the students start the cart at the bottom and give the cart a quick push so that it rolls up the ramp and momentarily comes to rest. The x-axis is defined parallel to the ramp once again with the origin at the top. So this is origin, this is plus x. In the following graph, sketch the position of x and velocity as a function of time that corresponds to the scenario shown. Okay. One thing is clear, that x is always positive because x is not going beyond the top of the ramp, otherwise we'll just fall. It doesn't make any sense. So we know that x should be positive in nature. Now at t equal to 0, can we agree that x is maximum because it is at the maximum distance from the origin, right? So can we agree that the curve of x should start from somewhere here? And what will be the shape? Well, remember that x is equal to, we already wrote that, v initial times t plus half at squared. That's going to be a parabola, right? We do not know where it stops. Maybe at the top of the ramp, or maybe not, maybe somewhere over here. We do not know. So we are going to make a parabola like this, and we are going to make it a stop maybe somewhere over here, where t equal to, let's call it t naught, is the time when it reaches the topmost point. And obviously eventually it is going to come down, so its x is again going to increase. That makes perfect sense. So it will again increase in that particular, I just overshot the axis given, so I'll just make perhaps like this. It's going to be a symmetric curve with a minimum value at t naught, where this is the point of the momentarily, when it momentarily comes at rest. And for the velocity, remember the velocity is going to be v naught or v initial minus at, which is going to be what do you call it as, a straight line, of course. B is equal to v naught plus at. That's going to be a straight line, and its what do you call it as, its initial sign is going to be, sorry, this should be plus at. Its initial sign is going to be negative. Why? Because the velocity is initially pointing towards the minus x-axis, and also it momentarily comes at rest also at t naught. So we have to make sure that it was negative initially. We have to draw a straight line. So we draw a straight line like this till this point where it is 0 at t naught, and then it will come down from here again. So its velocity will increase linearly once again after this point. So it will just keep going like this in this particular fashion when it is once again comes to the same point, right? This was the last part of the FRQ. I hope it makes sense. This is question number 3, the easiest question in the complete AP Physics 1 2023 paper. This is the easiest, and it will hardly take 5 minutes to solve this question if we know about the concept. This is based on circular motion and some spring forces. Let's read this out. A small block of mass m0 is attached to the end of a spring constant k0. So we have the spring constant k0. This is where we have a small block of mass m0. So this guy is, okay, just one second. Yeah. All right, this guy is m0. This is k0, And this is on a horizontal table, and a rod is attached to a motor that can rotate at various speeds, because there's a motor to it, so it can rotate at various speeds about its own axis. When the rod is not rotating, obviously the block is at rest and the spring is at its unstretched length L, so this is its natural length, and all the frictional forces are negligible. That's a relief. At T1, one scenario is given. So at time t equal to T1, the rod is spinning such that the block moves in a circular path with a constant tangential speed V1. So its tangential speed at this instant is V1 when it is rotating at some angular speed which we do not know, but we know that its stretch from the natural length is D1. Likewise, in figure 2 over on the right side, at time t equal to T1, the rod is spinning such that the block moves in a circular path with again a constant tangential speed V2, which we again with an elongation of D2, and once again we do not know the value of omega, but there is some omega, some different omega, which we for sure which we know for sure it's different. We know that D2 is greater than D1, fair enough. So the question one says, I'll just try to zoom this in since we are through with these two images. Let me zoom this size a little bit. Yeah. Now they are saying that on the following dots, which represents the block at the location shown in the figure 1 and 2, draw the force that is exerted on the block by the spring at the time T1 and T2. The spring force must be represented by a distinct arrow starting on and pointing away from the dot. Relative lengths of the vector to reflect the relative magnitude of the force is exerted by the spring at both the time measure. So it means that we have to draw, in other words, we have to draw in a force exerted by the spring in situation 1 and in situation 2, keeping in mind that their relative position matters. So we have to show that which one is high and which one is higher force and which one is the lower force, which is pretty straightforward. Why? Because what is the spring force? If you can remind me, what is the force of the spring? Force of the spring is of course kx, right? And what is x? X is not the total length, please mind it. X is only the stretch. So in case 1, the stretch is d1. In case 2, the stretch is d2. The value of k is k0, and it's already given in the question that the value of d2 is greater than d1. So this makes perfect sense that between fs2 and fs1, obviously fs2 should be more because k0 is same in both of them and d2 is greater than d1, so fs2 is greater than fs1. So all we have to do is draw two vectors, and of course where is the direction? Whenever the spring is stretched, the spring has a pulling tendency, so the force in both the directions will in both the cases will be over here, over on the right side. So I'm gonna draw, maybe starting right from the center, I will draw, let's call it 1 2 3 3 units on the right side in case 1, and then the right one I'm gonna make 1 2 3 4, maybe 4 units on the right side. The idea behind 3 and 4 is just to indicate that the right one is obviously a greater force than the left one. That is the only idea. So it should be very crisp and clear in our drawing to show that we are clearly showing that there is a difference in the relative lengths of both the vectors. That was pretty straightforward. And the next question, they are talking about referencing d1 and d2. Describe your reasoning for drawing the arrows the length you did in part A. So actually we already did that right over here, right? The work in the white one, that is the description for part 2, that since force of the spring is given by k0 times x0, so fs1 is k0 d1, fs2 is k0 d2. I'm just writing officially over here once again. Since d2 is greater than d1 implies that fs2 is greater than fs1, and that is the reason. Remember that AP Physics 1 is really picky about the way you write. The rubric is very important. So you have to show this work very clearly, that why you think that fs2 is greater than fs1. So this is the way you show the complete work. Okay. Now, the tangential speed v1 of the block at time t excuse me, at a t1 greater than, less than, or equal to the tangential speed as at v2, and justify your answer without using equations. I think it's pretty intuitive, right? V2 should be greater than V1 because the D2 is more, but remember that we cannot use any equations. So without using equations, I think I can say that the velocity V2, we know from the above part that Fs2 is greater than Fs1. Right, we know that. If the force is more, and we know that force is proportional to acceleration because the mass is constant, right? So can we say that the acceleration in S2 is greater than acceleration in S1? You might be wondering, why am I writing all this in the form of equation when they are saying without equation? We do not have to write equations, but all this which I am saying should be written in a coherent paragraph. I'm writing equations to make you understand. Let me write the equations first, and I'll tell you how we should have written that in the actual exam. So acceleration is more, and don't you think if the acceleration is more, obviously it makes sense that the velocity should be more, or angular acceleration or angular velocity, everything leads to velocity being more. So this is a very straightforward description without using an equation. So the way you're going to write is since force on situation 2, or maybe the figure 2 is greater than figure 1, this implies that and we can say that since as per Newton's law, Newton's law or Newton's second law, since force is proportional to acceleration, or maybe once again you can write an equation, a sentence over here, phrase over here, since force is proportional to acceleration, this means that this would indicate intuitively that this implies that acceleration of 2 is greater than acceleration of 1, which also implies that V2 is greater than V1. Right, so this is how you can explain this in a coherent paragraph. I hope this makes sense. And the next question, they're talking about, consider a scenario where the block travels in a circular path where the spring is stretched a distance d from its unstretched length L. Determine an expression for the magnitude of the net force F net exerted on the block. Express your answer in these terms. All right, that's pretty straightforward, because they are asking to find the net force exerted on the block, and the net force exerted on the block is nothing but k times, in fact k naught times x, right? And what is x? X is just the stretch, so k naught times d. That's it. That's the answer. Determine the expression for the magnitude of the net force exerted on the block. That's it. Because the spring force is the only force which is being exerted on the block. We can go back if you want to see the image once again. This is the block. Only the spring force exerts on it, which is a pulling direction. So it's just k times x naught, where x naught is the stretch. Stretch is d, so it's just k naught d. Write an equation for the tangential speed v of the block and express in these terms. Okay, so now we can say that the force which is exerted towards the center, the centripetal force, is equal to m naught v square over r, where we need to find the value of v. Now Fc is already given as k naught d, m naught is m naught, v is unknown, and r, be careful, r is nothing but, in fact I can draw a new image over here rather than doing back and forth. This is the pivot, this is where, in fact this is the mass, this is not the pivot, this is the mass, this is the spring, this is where it is being connected to a rod. Remember that its natural length is L and the stretch is D. So the radius will just be, this is spring all over, the radius will just be Radius will be the sum of d and l, right? The total length. So this is what we have to be careful about, that this should be d plus l. A little bit of rearrangement, multiplying d plus l both the sides. So k naught d plus l is equal to m naught v square. Dividing both sides with m naught, we have k naught over m naught d times d plus l is equal to v square, which means that the value of v is going to be square root of k naught over m naught d times d plus l. So I just took square root both the sides. So this is our expression in terms of m naught, k naught, l and d. There is no other variable as indicated in the question, only those variables. And the last question, I think, is, yes, this is the last question. Does your equation for the tangential speed of the block from part B agree with your reasoning from part A? What was our reasoning in part A? We were saying that since the force is more, acceleration is more, so the velocity is more. And let's see if the math agrees with us. So using this equation, can we say that if this d is more, because remember d is the only variable over here, k naught is fixed, m naught is fixed, l is fixed. So obviously it makes sense that if the value of d is even more, the velocity will be even more. So more is the value of d, more is the velocity, and this 100% agrees with our interpretation earlier. So just explain your reasoning. I just explained that since the velocity is proportional or not proportional, yeah, you can just write that since velocity is equal to root of k naught over m naught d times d plus l, and increases the value of d since the other parameters are constant. Since the other parameters are constant, will increase velocity. Since the value of d2 is greater than d1, this implies that v2 is greater than v1. Pretty straightforward. After question number 3, which I think is the easiest one, question 4th, the current question is the second easiest question in this complete paper. Let's talk about that. So we are given that there is a block of unknown mass which is attached to a long lightweight string that is wrapped several times around a pulley mounted on a horizontal axis through its center as shown. Okay, so this is the pivot or the axle, this is a disc, mass is m, radius of r, and this is a block which just hangs to it. Yeah, pulley is a uniform disk of mass m and radius r. Rotational inertia of the pulley is also given to us as half mr square. Pulley can rotate about its center with negligible friction. However, the spring does not slip. So string does not slip means that there is considerable friction and it allows it not to slip. On the pulley, as the block falls, when the block is released from rest and as the block travels toward the ground, the magnitude of the tension exerted on the block by the string is Ft. So the block is falling down, the tension is F of t, of course, in this direction. Here it's going to be right in the opposite direction like this. They are saying that determine an expression for the magnitude of the angular acceleration alpha d. Remember angular acceleration because the pulley is rotating like this with alpha d and the system is going down with an acceleration of a, which is not known to us, of the block as it travels downwards, and we have to express our answer as m, r and ft and any physical constant. So this is completely about the Newton's law, the equation of the force equations, and the torque equations. So the first things first, we know that the mass, the mass of the block is not known to us. Okay, so I think this is, maybe the Newton's law may not be too much helpful for us, but if you notice the pulley, this is the pulley and this is where the force is acting. So obviously this tension force is the force which is able to provide it the necessary torque, correct? Okay, and what will be the torque? We know that the value of the torque is R cross F. Fortunately here the R is definitely R, F is F, but the angle is 90. So cross product means sine 90 and sine 90 is just 1. So the torque is just going to be capital R times F of t. Also, the value of torque is given by I alpha. In this case, alpha is alpha d. And we already have the value of I, which is half mr square alpha d. This is also torque. This is also torque. All we have to do is equate both of them. So that's going to look like half mr square alpha d is equal to r times f of t. R times f of t. This r and this r is gone, and we are left with half mr alpha t is equal to f of t, which means that a little bit of cross multiplication and rearrangement will give me the value of alpha d as 2 times f of t divided by mr. So this is the value of the angular acceleration of the pulley, right? Okay, in the next question, and this is the last question of this part, this is the last part of this question. Here everything remains the same, so the scenario 1 is still that solid disk, the same moment of inertia half mr square, except for the point that the in the other scenario the solid disk is replaced by a hoop. What is a hoop? Hoop is just a hollow disk, so it's like a ring. It's like a ring. Okay. Its mass is same and its radius is same. Everything is same. The pulleys, the friction is also negligible about the center on both the cases. Now, in both the scenarios, the pulleys begin at rest, and then both the strings are pulled with the same force Fa for the same time interval delta t. So Fa is applied for the same time interval delta t, causing the pulleys to rotate without the string slipping. After the time interval delta t, the change in angular momentum of the disk is equal to the change in angular momentum of the hoop. So change in angular momentum of both the elements is found to be same, but the change in rotational kinetic energy for the disk is greater than that of the hoop. This is the observation. Question is very straightforward, that why this happens. So in a clear, coherent paragraph length response that may also contain equations and drawings, explain why the change in the angular momentum of both the pulleys is the same, but the change in rotational kinetic energy is different. So the concept over here, the first concept over here we have to use is the angular impulse. We know that the angular impulse delta L is nothing but tau times delta t. Just like the linear momentum or linear impulse is f times delta t, the angular momentum, the change in the angular momentum is tau times delta t. Delta t for both is same. And what is tau? What is the torque? Torque is just Fa, which is same in both the cases, multiplied with the distance, and the radius of both the cases is same, right? So the torque is going to be Fa times r. Why times r? Because the angle is 90, so sine 90 is 1. So we don't bother about the sine of the angle. So can we say that in both the cases, the change in angular momentum has the same value, which is Fa times r times delta t? And that is the reason why their angular momentum remains same. Okay. Initial angular momentum is 0, right? So right now we have answered the part 1, that why the angular momentum is same. Right now, now I'm moving to why the kinetic energy is different. Now we already know that the initial angular momentum is 0, of course. So Li is 0. And delta L is nothing but Lf minus Li, L final minus L initial. L initial is 0, so can we say that L final is actually the angular momentum, the change is equal to the final one. And don't you think that we also know of a formula for the angular momentum, that angular momentum is I omega. right? Just like torque is I alpha, angular momentum is I omega. So we know that the angular momentum for both is same because the change of both is same, and change is equal to final. So final momentum of both these parties are same. So LF of solid disk should be equal to LF of hoop, and L is I omega. So can we say that I1 omega 1 is equal to I2 omega 2? Okay. So can we say that I1 over I2 is equal to, all right, let's actually keep it like this. Let's actually keep it like this. If required, we'll manipulate further. Let's keep it and mark it as equation number 1. Now, what is the kinetic energy of the initial one? What is the kinetic energy, angular kinetic energy, sorry, rotational kinetic energy of the disk? So I will say that the rotational kinetic energy of the disk is going to be I1 omega 1 square divided by 2. Correct? That's the formula. Rotational kinetic energy of the hoop is given by I2 omega 2 square divided by 2. I'm going to manipulate this a little bit. Can I write it like this? I1 omega 1. This is going to be I1 omega 1 times omega 1 over 2. In fact, over 2 is over here. And this can be written as I2 omega 2 over 2 times omega 2. It's just a manipulation. Why am I doing that? Because this I1 omega 1 and this I2 omega, okay, let's do away with the square thing. I put a square over here. This I1 omega 1 and this I2 omega 2 are basically same, right, from equation number 1. So we are only interested to compare the value of omega 1 and omega 2. If we can compare omega 1 and omega 2, then we can justify that why the first one has a greater kinetic energy than the second one. I'm gonna make some space for myself. I think we are pretty much through with the green stuff, so I'm gonna erase this. And now I'm going to compare the moment of inertia. For this one, it's given as half mr square, and for a solid, for a hoop, the moment of inertia is very straightforward because all the mass is over here, which is at a distance of r. In fact, that's a pretty popular formula as well, that the moment of inertia is mr square. So we very well know that the value of I1 and I2, the value of I2 is more than I1, correct? So from this equation, can we actually say that since I2 is more than I1, and if we rearrange the equation which I just circled, this can be written as omega 1 over omega 2 is equal to I2 over I1, correct? Since I2 is already greater than I1, so here the numerator is more than denominator, and since the equation is since this is an equation, so same should follow for the left side as well. So omega 1 should be greater than omega 2. And isn't that what we wanted to prove? That if omega 1 is greater than omega 2, obviously the rotational kinetic energy of the hoop, sorry, of the disk should be greater than the rotational kinetic energy of the hoop. This is what we have to prove. So we proved this using obviously the moment of inertia and comparing their angular momentum as well. This is the last question, FRQ 5 of AP Physics 1 2023. This says that a rod with a sphere attached to one of the end of a horizontally mounted axle and carefully balanced so that it rests in a position vertically upward on the axle. So here we have the axle, and there we have a rod. A sphere is massed on the top of it, and it's carefully balanced so that it's just resting, vertically like this or like this. Now they are saying that the center of mass of the rod sphere system is indicated with a cross. So this is the center of mass. And the sphere is lightly tapped, so just a push is given to this sphere like this so that it just goes down, of course. and the rod sphere system rotates clockwise with a negligible friction about the axle due to a gravitational force. All right. A student takes a video of the rod rotating from the vertically upward position to the vertically downward position, while the figure 2 shows 5 names, still shots that the student selected from the video. So, the student made a video and took some stills at the 5 different position. These frames are not equally spaced apart in time, that's why. So, these are the 5 scenarios. Use the frames of the video shown in this figure. In which frame is the angular acceleration of the rod sphere system the greatest? Justify your answer. You're talking about angular acceleration. So angular acceleration means we need to talk about the torque. Okay. Torque is nothing but R cross F. We very well know that. Now R remains same, right? Whatever is the distance between the center of mass and the axle, it remains same in all the positions, right? So this is the value of this is the value over here. This distance is R and it points like this, and this is R here, R is here, R is here, R is here, R is here. So that's same in all the 5 cases. And the value of F is also same, right? Because its mass, whatever it is, it's not given, right? So let's say the mass is M. So mgx downwards here, mgx here, mgx here. In all the 5 situations, mg is constant. So the force is constant. So only thing which changes, we know that cross product is just sine of that angle. Only thing which changes, the only variable is the theta. And we want to maximize the angular acceleration. So in other words, obviously we want to maximize the torque, because more is the torque, more is the alpha, because the mass is anyway not changing. And what is the maximum angle here? It's pretty intuitive. It's 90 degree right over here. Otherwise, other angles are either acute or obtuse. It doesn't really matter, because sine is maximum when the angle is 90 degree right. So sine 90 is maximum, and this is in situation number C. So at C, we will have the maximum torque and maximum alpha at C, as angle is 90 degree and sine 90 is 1, which is the maximum value, right? In the next question, in which frame is the rotational kinetic energy of the rod sphere system the greatest? Briefly describe. Okay, so the rod energy, okay, let me just take I think I'm going to need this image on the next one as well. So what I'm going to say is that whenever we talk about rotational kinetic energy, and remember in this case there's no friction and all, so the energy is very well conserved. So if the energy is conserved, can we say that, and remember the system starts from rest, so initial kinetic energy is 0. So can we say that the situation in which there is a maximum decrease in the potential will result in a maximum increase in the kinetic? Because we know that, let's take the reference as this point, as the center, right? So I'm taking my reference as the axle. This is the reference. Obviously, the initial energy is mgh, whatever this height is. We do not know. Let's say the height is h. Now, I'm saying that if we conserve the energy, and here the kinetic energy is 0, so can we say that the total energy is actually mgh at such frame number A, which is the total energy? And when will the kinetic energy be maximum? When the potential energy is minimum now, which is in frame E, because in frame E the potential energy is minus mgh and the remaining energy will be kinetic. So obviously this kinetic will come out to be 2 mgh, which is the maximum in this case. Why maximum? Because in all these situations the potential is not going to a minimum value. It is some value more than the minimum possible value. So obviously the less change in potential will increase the kinetic with a less amount. That makes perfect sense. And more decrease in the potential will increase the kinetic energy by a greater amount. It's like the energy bars, if you remember. So the energy bar works like in situation number A, this is the complete potential and the kinetic is 0. And in situation number C, the potential is just negative of that value. So obviously kinetic should be maximum at this point because the sum of both the bars is constant, right? So that way is also it makes a perfect sense. So answer is frame number E because of minimum potential energy. All right. Okay, some dimensions are given to us that the center of mass is given to us as 3L/4 distance from the center. The rod sphere system has a mass m and L and the center of mass is 3/4 at L. Derive an expression for the change in kinetic energy of the rod, sphere, earth system from the moment shown in figure A to the moment shown in figure E. We just did that, right? Except for the fact that we didn't take this h into length into account. So all we have to do is go back, borrow this expression because that is eventually the change in the kinetic energy, because the kinetic energy at A plus potential energy at A is kinetic energy at E plus the potential energy at E. Kinetic energy at A is 0. Potential energy at A was mgh, like we said earlier. Kinetic energy at E is something which we need to find, and the potential energy at E is minus mgh. So the kinetic so adding mgh both the sides, 2 mgh is equal to the kinetic energy at E. This means that the kinetic energy at E, which is as good as the change in kinetic energy, because the change is Ke minus Ka and Ka is 0. If it is confusing to you this way, I will not replace Ka with 0. I will keep it as it is, and I will then move Ka over on the other side, so that now we are on the same page that 2 mgh is equal to delta K. So the value of delta K will be 2 mg, and the value of h is 3L/4 because that is the center of mass height. So the answer is 3 mgl, 3/2 mgl. That is the change in the kinetic energy. Pretty straightforward, right? All right. The last question which we have is briefly explain why the rod and sphere gain kinetic energy even if Earth is not included in the system. Okay, so mg is still acting, right? Mg is still acting, but now mg will be considered as an external force because Earth is not a part of the system, so we cannot say that the potential energy is mgh. Mg is just an external force, it's no longer an internal force. However, notice the work energy theorem. If you remember, work done by all the forces is change in kinetic energy. Now mg is an external force and mg is, let me borrow this image once again. Okay, now mg is an external force and mg is acting down like this continuously. And if you can help me, where is the displacement? Displacement is also down, right? Obviously some components and all are to be taken, but the force of mg is down, displacement is down, so the angle between the force and the displacement is acute, which means that the work done is positive because the work done is given by F dot d. Force and distance or displacement are in the same direction. It means that the work done has to be positive. So can I say that the work done by all the forces, and basically all the forces is just the gravitation force because that's an external force, is positive with this with what I just justified? And if it is positive, can we say that this is positive and this is equal to the change in kinetic energy? And if the change in kinetic energy is positive, it definitely means that the final energy is more than the initial energy. that then only the change can be positive. And hence this justifies the fact that then also, even though you won't consider the earth as a system, the rod and the sphere will gain the kinetic energy, as it moves down, because the change in kinetic energy is positive as the work done by the gravity is positive. Right, this was the last part of the last question. I hope it makes sense. I have made videos for all the 5 questions of AP Physics 1 2023 FRQs. Please check. Let me know if you feel like I have messed up somewhere or your thought process is different, you have done differently in your exam. Please post it down in the comment section. I'll try my best to answer. Thank you very much.